Okay. So with the partial adjustment model, we're working here with the model of gasoline demand for the United States. Now, just to recap on this, if we estimate a simple model, we get lots and lots of serial correlation. So if I run a regression here, so I type in LS for least squares, and I regress the log of gasoline demand on a constant, the log of GDP, and the log of relative price, okay, that's the equation that I get using eViews, and you can see that from the Durbin-Watson statistic here is extremely small, 0.055. Okay, so we're picking up a lot of serial correlation here. Okay, if we looked up the critical values in the tables, we'd find that we reject the null hypothesis. Now, the Durbin-Watson statistic is a valid test for serial correlation in these circumstances, because there's no lagged endogenous variable on the right hand side of the equation. However, suppose we respond to this by saying the reason why I might be picking up so much serial correlation is because agents aren't adjusting their gasoline demand to the equilibrium value all at once. Instead, they're adopting a partial adjustment strategy along the lines that we've got here. Yeah? So, suppose I estimate a partial adjustment model. Well, there's nothing to stop me doing that. All I need to do is add the lagged endogenous variable to the right-hand side of the equation, and I've effectively got a partial adjustment model of gasoline demand. So I can do that quite straightforwardly here by clicking on the estimate button, and then in the dialog box here I can add the lag of the endogenous variable. So I can add log motor minus 1. Okay, hit return, and it re-estimates my equation, but now you see including the lag of the endogenous variable here. Okay, now this is kind of interesting. If you look at this, it's changed the regression equation quite significantly. The log of GDP is no longer significant. The T ratio has fallen well below the critical value here, which is about 2. Relative price appears to still be significant, and then my lagged endogenous variable has got a coefficient that's very large, 0.93, so it's close to 1, and a very large T statistic, 36. Okay? Has it cured the serial correlation problem? Well, if I click on the resids, okay, the residuals do appear to be more random than they were previously. They change sign far more often than they do with the basic model. However, there's a problem here that we can't use the Durbin-Watson statistic as a formal test for serial correlation. See, normally, if I wanted to test whether or not there was still serial correlation in this model, what I would do is I would go to the Durbin-Watson statistic here, 1.35, then I would go to the critical value tables, and I would check whether or not this lies within the critical bounds, and if it lies outside the critical bounds, I would conclude there's serial correlation. The problem is I can't do that here, because the presence of the lagged endogenous variable in the model means that the Durbin-Watson statistic is biased, and as a result I'm not going to be able to use that test. Hence, I need to develop different tests for these circumstances when I've got lagged endogenous variables in my model. So what I'm going to do now is go back to the slides, okay, and look at a couple of extra tests. Okay, so let me start again on that. What I want to do is carry out the Broich-Godfrey test for serial correlation for the gasoline demand model that we've been estimating. And to make this a little bit more general, what I want to do is a test for second order autocorrelation rather than first order autocorrelation. So the first stage is I need to estimate my model. So I've already got that on the command line, so if I hit return here, it estimates my model. Okay? Now, the neat thing about eViews is it will do all the hard work of the Boyce-Godfrey test for you. You don't have to go through all those procedures we did on the previous screen. Instead, we go to View, Residual Diagnostics, and then we look for Serial Correlation LM test. So I click on that. It asks me how many lags to include. So I want to do a test for second order autocorrelation here, so I'm going to take the default of 2 lags. So click on OK, and what it does is estimate that auxiliary regression, okay, and it does the test for me automatically. Okay, so this is my auxiliary regression here. It's regressed the residuals on a constant, the original regressors, log GDP and the relative price, and then 2 lags of the residuals. Now what we're doing is a test for the joint significance of these 2 lag residual terms here. Okay? And there are 2 forms that the test can take. Either a chi-squared test, which is equal to the number of observations multiplied by the r-squared from this auxiliary regression, and that, under the null hypothesis, that test statistic is distributed as chi-squared with 2 degrees of freedom. Okay? See, and the test statistic of 49.1, the critical value is just under 6, 5.9 something, so clearly that rejects the null hypothesis. Secondly, we can do an F-test. Now the F-test again is based on the joint significance of these 2 regressors here. We get an F statistic that it's computed for us of 181. Under the null, that's distributed as F with 2 and 51 degrees of freedom, and again we see that it's highly significant. So there's still evidence here, or there is evidence here, of autocorrelation. Okay, now let me see if modifying the model to allow for a partial adjustment process removes the serial correlation. So if I go back to my regression equation here, okay, and click on estimate, then I know already that this is a flawed model, that it's got lots of serial correlation. So instead of just assuming a static relationship between these variables, what I'm going to do is I'm going to include a lagged endogenous variable to allow for partial adjustment, to allow for a spreading of adjustment towards equilibrium over time. So I'm going to put in here the log of motor minus 1. Okay, and we get this equation here. Okay. Now we've seen already when we estimated this equation before that it did appear to get some improvement in terms of the serial correlation properties. The errors, if we click on resids, okay, change sign far more often. Okay, so we get much more a much more random looking residuals than we did from the original model. Okay, the problem we have is that when we want to do the formal test, we can't use the Durbin-Watson statistic here because we know that because of the presence of the lagged endogenous variable, the Durbin-Watson statistic is biased towards accepting the null hypothesis. It's biased towards 2. So instead, we use the Boyce-Godfrey test. So if we go to now View, Residual Diagnostics, Serial Correlation Test, and now I'm just going to do a test for first order autocorrelation here to show you that we can do essentially the same test as we want to with the Durbin-Watson. So I'm going to change that to 1. Okay, what do I get? Well, again, you see what we've done here is we've estimated an auxiliary regression. So we've regressed residuals on a constant. Now the 3 endogenous right hand side variables here, exogenous variables, plus the lagged residuals. We then compute the 2 tests for serial correlation. There's a chi-squared test here, okay, test statistic of 5.13, Under the null, that's distributed as chi-squared with 1 degree of freedom. So the p-value of this here is 0.02. It's well below the critical value of 0.05. So we would reject the null hypothesis still in this model. Similarly, with the f-test here, we've got an f-test statistic of 5.14. Under the null, that's distributed as f with 1 and 50 degrees of freedom. If we were to look at the critical values in the tables, we'd find that, again, we're still rejecting the null hypothesis here. Okay? So, anybody any questions on that? Okay. Right. Well, what I'm going to do is move on to the last couple of slides on serial correlation, and then we'll take a break, and when we come back we'll do the material on heteroskedasticity. So let me go back now to the slides here. Okay, and what I'm going to do is take a cross-section data set and use this to apply the heteroskedasticity test that we have been discussing here. Okay, so how do we, I'm going to load up my cross-section data set, and it gives me a chance to do a little bit of revision with you, because I've actually got this stored as an Excel worksheet. Okay, so I'm going to input it into eViews from an Excel worksheet. So to do that, I go to File, Open, and then Foreign Data as Work File. Now this is my default directory here, and in that I've got an Excel worksheet here which is cross-country inflation data. Okay, I'm going to open that. Okay. And again, because this is a Excel worksheet, it will need to check the structure of it, so it tries to look for whether or not how the data is structured. The data's in columns here: inflation, money growth, and GDP growth. So it's all okay. So I'm going to click Finish, and it's going to import it there. Okay. So what am I actually testing here? Well, basically, what I'm going to do is I'm going to test a version of the quantity theory of money. Can I take a show of hands? How many of you are familiar with the quantity theory of money? Yeah, one or two of you. Okay. This is one of the oldest theories in economics. Basically, the idea is that ultimately what causes inflation is growth of the money supply. Okay? And basically, what we're going to do is to look at the relationship between inflation and money growth. And I've got a sample here of 83 countries, and for those 83 countries I've taken the average rate of inflation over a long period of time, okay, over 10 years. So I've got a cross-section of data for different countries, and it's an average of inflation over a long period of time, and also an average of money growth and real output growth over the same period of time. And what I want to do is to estimate a version of the quantity theory of money. Okay? So how would I do that? Well, again, going back to my eViews here, I go to Object, New Object, Equation, and my dependent variable is going to be the rate of inflation. So I'm going to type in here inflation, and then on the right hand side I'm going to have money growth, and I'm also going to put in GDP growth, because GDP growth is potentially important as well in the quantity theory. So I'm going to have here money growth and GDP growth. Oops, sorry. Okay, and hit return. Click on OK. That's my basic regression equation. Okay, so remember we're dealing with cross-section data here. This is different from our time series models before, so things like Durbin-Watson don't really mean anything here. Okay, so how do we interpret this? Well, if we look at the results, we see that we do appear to get a very significant coefficient on money growth with a coefficient of just over 1. Okay? So for these 83 countries, there is a systematic relationship between money growth and inflation, and there's more or less a 1-for-1 increase in the average rate of inflation with the average rate of money growth. Okay? So to that extent, this model is consistent with the quantity theory. Okay, now, this is exactly the sort of data set where we might get heteroskedasticity. We've got cross-section data. We've also got a large variation in the rates of inflation across these countries. Some countries have typically got very low rates of inflation. Other countries have got very high rates of inflation. So, how would I test for autocorrelation? How would I test for heteroskedasticity? Well, the answer is I can use the White test. The Goldfeld quant test would require quite a lot of work here, so I'm going to avoid that and just go straight for the White test. So I go to View, Residual Diagnostics, and down here, Heteroskedasticity Tests. So click on that, and there are actually lots and lots of alternative tests built into eViews here. The one I've described to you is the White test, so I'm going to move down to that. Click on OK, and it's done essentially what we showed before for the profits example. Okay, it's taken the residuals from my model and it's squared them, then it's regressed the squared residuals on money growth squared, money growth times GDP, that's the cross product, money growth, GDP growth squared, and GDP growth. Okay. We then do either an F test or a chi-squared test, okay? And in both cases here, we get for the joint significance of these right-hand side variables. In both cases, we are going to reject the null hypothesis very convincingly. Okay. For example, for the chi-squared test, we need to compare that test statistic of 28.6 with the critical value for the F test, for a chi-squared test with 5 degrees of freedom. Now if I look that up in the tables here, okay, for a chi-squared distribution with 5 degrees of freedom, the critical value, the 5% critical value is 11.07. Okay, so clearly a test statistic of 28.6 is well above the critical value for a chi-squared variable with 5 degrees of freedom. Okay, we could do the same for the F test. We could look up the critical values in the tables, and again we'd find that we reject the null hypothesis quite convincingly. So there's evidence here of heteroskedasticity. Anybody got any questions on that? Right, now what do we do about it? Well, dealing with heteroskedasticity is often quite tricky. Sometimes we can scale the data, okay? As I suggested earlier, we might look for a scaling of the data, but it's not very easy here. There's no obvious way of scaling this data in order to remove the heteroskedasticity problem. But there is another alternative available to us. Remember, the main problem with this heteroskedasticity is it's going to bias the standard errors of the coefficients. It's not necessarily going to lead to bias in the coefficients themselves, it's just going to lead to misleading results because of the standard errors being biased. So what we can do is we can use an adjustment to the standard errors which actually compensates for the presence of heteroskedasticity. I'm not going to crank through the details of this with you, I'm just going to show you how to do it. Basically, if I go back to estimate here, okay, that's the dialog window for estimating my model. So far, I've just used that straightforwardly. I've not taken any options here, but if I click on options here, there are a series of potential options, okay? So basically, what we've got here is we've got the coefficient covariance matrix. It's the estimation default, but if I bring that here, I can instead look at what's called the white covariance matrix, and this adjusts the standard errors for the presence of heteroscedasticity. Okay, again, it's down to Hal White, who did a lot of work on this. So I'm going to opt for that. Click on OK. Now it re-estimates my equation here, and although the coefficients haven't changed at all, the coefficients are exactly what they were previously, you will find that the standard errors have changed and the t-statistics have changed. So adjusting for the presence of heteroscedasticity, adjust the standard errors for the presence of heteroscedasticity. Okay? And this will lead to more reliable results, or more reliable statistical inference, because we won't be using standard errors that are biased. Okay? Or hopefully we won't. None of these procedures are in practice perfect. Okay, so if you come across a situation like this where you're estimating a model, particularly a cross-section model, you find evidence of heteroscedasticity, what I would first of all recommend you do is re-estimate the model and look at it with the white standard errors, or the adjusted standard errors, rather than the standard least squares standard errors. So these are the white heteroscedasticity consistent standard errors. Okay? So I recommend that as being your first thing to do. Okay? If that doesn't solve your problems, you may have to go and rescale your data, but that's a far more complicated procedure. Okay, so what we're going to do is go back to the slides and consider one final form of heteroscedasticity. To the visualizer here, and we're going to actually carry out an arch test of the kind that we've described. Okay, so let me go to open up the data file that we were working with yesterday. This is the daily equity price data, and what we typically find is that this is exactly the kind of data set where we detect this kind of problem, okay, because it's high frequency financial data. So what I'm going to do is estimate the market model for Vodafone that we looked at yesterday. So I'm going to use the command least squares dlog Voda on a constant and dlog FTSE. Okay, and I get my familiar, or from yesterday, market model, where this is my beta coefficient. This tells me how the return on Vodafone varies as the return on the market as a whole changes. Okay. Now, I believe that there is there's at least the possibility of what we call ARCH, or autoregressive conditional heteroscedasticity here. So to test for that, I go to View, Residual Diagnostics, again heteroscedasticity. And one of the options here is ARCH. Okay, click on OK. And this does the auxiliary regression and test that we talked about earlier. So basically it takes the residuals from my original model and it squares them and regresses those squared residuals on a constant and the lagged squared residuals. We then do a test for the significance of these lagged squared residuals. There are two tests here. There's a chi-squared test and an F test, and both of these are telling me that I've got significant arch in the residuals. So I've got significant autoregressive heteroscedasticity. Okay, again, detecting something is easier than actually dealing with it. So what I want to finish today's lecture by doing is just basically showing you how you could actually deal with this by actually estimating a model that explicitly includes arch. So if I go back to my equation here. If I click on stats, it will go back to my original model. I know now that there is autoregressive heteroscedasticity in these residuals. So, in order to get more reliable estimates, I'm going to explicitly deal with that in the estimation procedure. So I click on estimate, okay, and then go to the method here, okay, and under method, instead of least squares, I'm going to opt for autoregressive conditional heteroscedasticity, or ARCH. Now, as I said on the board earlier, the most common form of ARCH is what we call a generalized autoregressive heteroscedasticity, which takes the form of the equation that we've got on the whiteboard over there. That's what I'm going to estimate here. So this is the default here, with an ARCH term of 1 and a GARCH term of 1. So if I click on OK, it estimates that model. It reports to me now two equations, a mean equation, which is my standard market model. You notice that the beta coefficient here has gone down a bit, okay, still above 1, but it's changed a little bit. And then we've got a variance equation, which is the equation that we talked about earlier. Okay, it's basically that equation that's on the whiteboard over there. Okay, we've got the variance being regressed on a constant, the lagged squared residual, and the lagged GARCH term here. Okay, you can see that those terms are very highly significant. So that's how we might at least try to deal with the presence of GARCH, by actually estimating the model that includes it. Okay, that is actually pretty much it for me. So